Okay, couldn't really find a good video on this, and it's calculus based, so I'm going to go through this in a little bit of detail, but wanted y'all to understand where the uh, numbers come from for moment of inertia, like for instance a solid sphere. You remember the definition of the moment of inertia of a point mass was just mr squared, where r is the distance from the point that it's rotating about, and m is the mass. If you had a bunch of point masses, you just do a summation of all of them. So it would look like this if you had a bunch of point masses. So you could imagine if you had a bunch of little mass elements, like in calculus, then this would simply become the integral of r squared dm over the whole volume, or over the whole mass, if you would. But mass is contained in a volume. And you know the relationship between mass and volume. We call that density. And in physics, we use the Greek letter rho, or some people say rho, or whatever, but I'm from Kentucky, so I'm going to say rho. And it's the mass total. This would be total mass per unit volume. So this would be like a capital M if for a solid of uniform density. What would they say? Isotropic and homogeneous and all of that. The bigger the objects get, though, you need to realize, like a planet, the gravitational pull will cause that density to get greater and greater towards the center. Even for things like iron that you would think would not be very compressible, they get very compressed towards the center of a planet. So the density would increase the further you go. But a small object like a ball or steel ball or something like that, if it's solid, we'll assume it's of uniform density. Because I said we'd talk about a ball, a spherical ball, and this is going to be awful. I can't draw circles very well. Probably as close as I'm going to get. We'll set up a set of axes, X, Y, and Z axis, like this. This would be X, Y, and using the right-hand rule, this would be Z. So you turn, Z would point up. And let's pick some little mass element out here, and let's pretend, well, you don't have to pretend, imagine this thing rotating about the z-axis. So we're going to take the moment of inertia as this thing spinning about the z-axis. We could align the axis up anywhere. Take a little piece of mass out here somewhere, little mass element, dm, and it is rotating about the axis right here. This r is this r. This would be the r, okay, that is in that equation. This is going to be a little complicated because I want to use spherical coordinates, and so I want to know this object's position relative to the center, the angle from this axis, which we normally call phi. And if we drop this down in the xy plane, like this, we call this angle theta. And this thing's going to rotate around like this. I'm trying to make it is really hard to get the graphic in 2 dimensions so it makes sense. So the sphere is going to rotate around the z-axis. This point is above somewhere in the xy plane, I'll say in the first quadrant. This is theta. That's phi. I need to give this position here, that's third coordinate. We have 2 coordinates. You had to have like x, y, and z. In spherical coordinates, you normally use rho, theta, and phi. But I'm using rho for density. It gets awful confusing. And I'm using r for the axis here. So I'd sort of need another letter to use for this that is like a position there that is not rho or r, because you know most of the time we're going to use rho for that, r for this rotation. So how about I use a pretty r, like a cursive r, like this. So our coordinates then would be r, theta, and phi. That's the spherical coordinates. Now, if you had any calculus, well, that's not true. This is not Cal 1 unless you're in Germany or somewhere, like Cal 3 in college maybe. You would get to multivariable calculus. The volume element here, instead of being dx, dy, dz, you'll probably remember is r squared. This would be the pretty r, sine phi, d phi, d theta. Now I'm not going to go through the process. You can look it up online to see how you get this as the volume element, but you have to realize this volume element up here, shaped like this. This arc length right there is going to be pretty r times this angle that it goes through, which would be delta phi. And so you can see how you get an r delta phi for this side. And then when you multiply the three sides to get the volume, this is what you get. I'm not going to go through that in detail. You can look it up. All right. So back to finding the moment inertia of this solid sphere. Keep in mind this is a solid sphere of uniform density. This is not for a hollow sphere. So let's look at the integral of r squared dm. Well, notice what this r is. It is pretty r sine phi. So this r becomes pretty r sine phi. And that's got to be squared dm. I'm going to try to get all this on one page if I can. Sorry that my camera's shaking. I'm shaking my table. That's probably irritating for y'all. So dm. Well, dm is going to be, if you look at mass, volume, and density, dm is going to be rho dv, where dv is the volume element. So let's put that in. So, and seeing as I'm putting this in, I'm going to go ahead and put in the limits of integration for all three of those variables while we're here. So we have r squared sine squared phi, that's that squared, dm. That's going to be rho, but it's just a constant, so I'm going to take it out here for right now. And then we have, this is pretty r squared sine phi. Oh, did y'all notice I left something out here? dr. So sine phi d phi d theta d pretty r. Okay. Now let's look at what we'd have to integrate over. Well, obviously the r1 here, we're going to integrate from 0 to capital R, which would be the radius of the sphere. Let's make the total mass capital M. Okay. So the density here, like I said, would be capital M. Volume, though, 4/3 pi capital R cubed. So keep that in mind. We'll use that later on. Theta is going to go all the way around, right? 0 to 2 pi. And phi is going to go from 0 to pi. Okay. Some of this won't be too hard to do. So let's do what we can, and then we'll work from there. So let's do the integral. The easiest one's obviously theta, because you integrate d theta, you just get theta. So we can do that one first. We get, and I'm going to use notation here, just be theta evaluated from 0 to pi. Let's go ahead and do pretty r while we're here. R squared times r squared dr, that's r to the fourth. So the integral of that would be r to the fifth, pretty r, sorry, to the fifth over 5, evaluated from 0 to capital R. We still have this row out here. And now we're left with the integral from, let's see, I'm sorry, this went to 2 pi, 0 to 2 pi on theta. Then we still need to integrate the phi from 0 to pi of sine cubed phi d phi. Okay, you could just look that up in an integral table if you wanted to. Probably wouldn't hurt for me to go back and refresh your integration by substitution, because we could do a substitution here. So let me do that. I'm going to make the substitution that u, some function u, is cosine phi. Du then would be a minus sine phi d phi. Okay. Our limits of integration then would be u of 0 will be 1, right? Put 0 in here, you get 1. And u of pi, negative 1. So our limits of integration will change from 1 to negative 1. All right. Let's do a little manipulating here. And I'm going to go ahead and evaluate this. We get 2 pi r to the fifth over 5 and rho. So that takes care of all of that. And we're going to evaluate this integral now. But before I do the substitution, let me write this as sine phi sine squared phi, like this. Okay, d phi. This, if you remember, is, and I'm going to combine a lot of this stuff here. I'm going to have 2 pi rho r to the fifth over 5, so I can write that all as 1. And then this phi still goes from 0 to pi, sine phi 1 minus cosine squared phi. Oh, I ran out of paper. d phi. Okay, because sine squared phi, 1 minus cosine squared phi. Same thing. Got to remember that from your pre-cal probably. Okay, so now I'm going to make my substitution here. I'm going to substitute in for cosine phi u. I'm going to substitute in for sine phi d phi a minus du. Okay, so I hope I don't mess up the algebra here. Been a while since I looked at this. So I am going to change my limits of integration now from 1 to minus 1. And this becomes, like I said, sine phi d phi is a minus du. So there's a minus du right here. And then 1 minus cosine squared phi becomes 1 minus u squared. Like that. Okay. That doesn't look too complicated now. It'd probably be good to take the minus sign out here. So let's see about that. Ooh, I'm getting all jammed up here. Okay. So we have 2 pi, the density, r to the 5th over 5, and I'm going to take the minus sign out. We have the integral from 1 to minus 1 of 1 minus u squared du. This integral you can probably do. The integral of, because you could just do the integral of du and the integral of a minus u squared du in these limits. In other words, distribute this through and just do the integral. So you get, when you do that, now I could just swap the limits, and I could use the idea that this has symmetry, so I could just do 2 times the integral from 0 to 1. That would definitely make it the algebra a little bit easier than having a bunch of minus signs. But let me see if we can do it without doing that. So we have 2 pi rho r to the 5th over 5. I'm going to evaluate this now. We have a minus u plus u cubed over 3. That's the integral of these, evaluated from 1 to negative 1. Okay, so let's do that. Let's do the evaluation there. This may get a little messy. I hope I don't run out of paper. So if you substitute in 1, well, you do the upper limit first. Negative 1. So we get 1 and a minus 1/3. And then the lower limit, 1 and plus 1/3. Like that. Let's make sure I didn't do anything wrong. Lower limit. Did I leave off this negative? Makes that positive. Nope, I think I'm good. All right, so we have 2 pi rho r to the 5th over 5. And in here, we have, let's see, we have this 2, and we have a minus 1/3 and a minus 1/3, that's 2/3. So 2 and 2/3. 2 and 2/3. 5/3? Is that right? 2 and 2/3. 6, no, it's more than that. 2 is 6 plus 2, 8/3. 8/3. Hope I didn't mess anything up there. Be a lot of work for nothing, wouldn't it? All right, so let's substitute in for rho. The mass, let's see, I'm gonna put the 5 under here so this gets a little easier. Substitute in for rho, m over 4/3 pi capital R cubed. Then we have this r to the 5th, and then we have this 8/3. Wow, this is ugly. But fortunately, a lot of it cancels. This r to the 3rd cancels, makes that a 2. Let's see, this 4/3 on the bottom and this 8/3 on the top. Let's see what happens there. Okay, so let's take out the pi's first, make it a little better. I'm off by a factor of 2. So these 4/3 and that 8/3 should cancel. What did I do wrong in here? We have 1 plus 1. Make sure I put those limits in right. We put a negative in here, we get a positive 1. Put a negative in here, we get a negative 1/3. Subtract from that, putting a 1 in here, we get 1, a negative 1, sorry, negative 1. And we put a 1 in here, we get 1/3. Okay. 1 and a positive 1, that's 2. A negative 1/3 and a negative 1/3 is, there it is, negative 2/3. 2 minus 2/3 instead of 2 plus 2/3. Okay, so that becomes a 4. That cancels that, and our end result is 2/5 mr squared. So the moment of inertia of a solid sphere, 2/5 mr squared, assuming uniform density. And this shows you how minus signs always mess you up. That's why I said it'd been probably easier for me to use symmetry and just double this, which would have got me that 4/3. Hope that helps you see where the moment of inertia of a solid sphere comes from. A little complicated, but you realize that the moment of inertia is strictly something that deals with the space and how the mass is occupied in the space. So it's a dimensional thing. It has nothing to do with whatever forces or torques are being applied. It's simply a matter of geometry and how that mass is distributed over that geometry. Hope you enjoyed that. If not, maybe it'll put you to sleep.